We're looking for what time, what dot what? The gradient of f at 3, 1 dot what? U. Well, we have u, so all we're looking for now is f of the gradient of f at 3, 1, right? So the gradient of f at 3, 1 is equal to, it's a vector, correct? It's fx 3, 1, fy 3, 1. So what do we need to find first? We need to find those two values. So we need to estimate them.
Which we found earlier.
Did they?
For these problems.
You found, well, they're different vectors, right? For these, yeah. I mean, these. I mean, for 55 or 56.
53 and 54.
Yeah, 53 and 54. You found. Oh, you found them. No, you didn't find them because fi is the directional derivative in the I direction.
Okay.
Fj is the directional derivative in the j direction. Do you understand? So hold on, let me show you what I mean here. But basically, and you've already touched on this, and I already responded a little bit, it all comes down to how you calculate this given the picture. So let's just talk about the two different ways, the way the book will do it and the way I'll do it. And I think the book is a little bit more correct than I am. I'm just kind of stuck in my ways a little bit, and maybe I should change. Either way, though, one thing that's annoying is that picture that I put up there, that point is not the actual point. What point are we actually looking at? 3, 1 is right here. My version, I think, uses a different value for the question. It centers it at 4, 1, yay, whatever. So the way the book does it, I'll show you what the book does. So if you're doing fx, that means you're fixing y. So if you're fixing the y value, you're looking at a horizontal line like this, right? They go from, in the book, they start with the point here and they go to this next point. So in the book, they do fx 3, 1 is equal to 2 minus 1 over 4 minus 3. So 2 minus 1 over 4 minus 3. So they end up with 1 over 1, which is 1. And then when the book does fy, they're not consistent. I would think like if you're going to start at the point and go forward on this one, they would start at the point and go forward on the other one. It's a little bit harder to do that because you end up hitting the 1 again and making it 0. So instead, what do? They estimate like, sorry, they take like this point right there and go to that point. So they estimate it. So what do they do instead? So they do, what is that, 2. So they do 1 minus 2, this 1 minus the 2. Is everybody with me in the output of those? But then they have to estimate the bottom part, right? So they estimate it as 1 minus like, like 0.4 or something like that. I mean, you have to, when I say 0.4, they're estimating what this x value is. Like maybe it's 0.4. Great. So then they get negative 1 over 0.6. So like negative 1.67, you know, depending on how you round it. So that's what they get. So then what do they do with those values? This right there tells you what the gradient vector is. So the gradient of f, and I'm dropping letters, the gradient of f3, 1 is going to be equal to 1 comma negative 1.67. So then what do you do with that vector? You dot it, exactly, times the u vector, which was what? Negative 2 and what? 1. And then what's on the outside? Root 5.
But in the book, I'm pretty sure you got negative 1/2.
Oh, for the second one?
Yeah.
Maybe I did the math wrong. Yes, I understand it's kind of frustrating because you like being able to like match the exact decimals in the book. It's just not going to happen sometimes. The message here, know the method. Know the method. And hopefully the examples I give you won't give wildly different answers based on like which points you pick. Do you understand what I'm saying? Yes. What's the first thing you should find? Okay, you're doing a directional derivative, so you're doing the dot product of the gradient and the direction you want to go in. So what do you think the first thing we should go after is? The gradient. The gradient itself. So let's find the gradient. So to find the gradient, what do we need to compute first? fx, x, y, z, right? fy, x, y, z, and what? fz, x, y, z. Exactly. So if you do fx, what's fx? Just y. What's fy? And what's fz? 2z. So then what are you plugging in? 2, 3, 4, right? You're plugging in that point into there. So what do you get out? You get, so fx at 2, 3, 4 is 2. No, I did the wrong value. Thank you for the catch. It is 3. You're like, we want to believe you, but you're wrong. So what's this is going to be 2. And then fz is going to be what? 3, 4 is 8. Okay, so we know now, what do we now know? We know that the grad f at 2, 3, 4, 2, 3, 4 is what? 3, 2, 8. The gradient is a vector. So in order to find this directional derivative, we need the direction as a unit, correct? So this vector, 3, 2, 8, the direction we want to go in, what do we know about it? The direction of a vector making an angle of 3 pi over 4 with the gradient vector. Well, we know what the gradient vector is, right? Just for those of us that maybe don't visualize radians that well, what's 3 pi over 4 in terms of degrees? Is it 135, right? Because it's, wait, 3 pi over 4 is 135? Yeah, because 180 is pi, so you go back 45 degrees. You're absolutely right. That's 135 degrees. It's fine. Okay, so how do we go? I'm actually stumbling to find a good answer. It's the magnitude of the first vector, right? Dot what? Sorry, times the magnitude of the second vector times what? Cosine of theta, exactly. Good save, Nate. So, but what is the magnitude of u? 1. So what are we really just doing? The magnitude of the gradient of f at the point we want, right? Times cosine of. So if we want this, f in this, we'll call this direction, we'll say this direction, what letter do you want to use? W, is that okay? So fw, what's that going to be? The magnitude of 3, 2, 8. Is that correct?
Yeah, it's root 77.
Times cosine of 3 pi over 4. So it's going to be the square root of what?
Root 77.
77.
And then it's negative 1 over 2, so it's square root 77 over 2.
Negative 1 over what?
Root 2.
1 over root 2, right?
Yeah.
Yeah.
Because the 2 goes.
Yeah, so negative root 77 over root 2. Is that good?
Yeah.
Does that make sense?
Yeah, pass it as 77 over 2.
That's fantastic. Now, I guess the repeated lesson the book is hammering us with is don't just remember the algebraic definition for dot product, also remember the geometric. Because I was about to think, man, if I had to find the vector, angle measure, 135, cosine inverse, I was going to like disassemble the algebraic definition to find the vector, and that was way more than we needed. Good save, Nate. Good save.
Why do they bother?
We could have z in terms of f having 2 input variables. Z could be f comma x, Sujong. But instead of x being just a singular value, x could be written in terms of some function in terms of t, and y could be written as some function in terms of t. You've seen functions written in terms of t before. What are those called, Nate?
Functions in terms of t?
Yeah, we've seen functions in terms of t
Do they have
before.
to do with, like,
What's
time?
yeah? What's the general name for those we've used in the past?
Rates?
Nope. What are they called? What kind of functions? Parametric equations. We've seen parametric equations where it gives you not only the path of the particle, but it tells you when the particle is at each point. Do you remember parametric equations? You'd have like x equals t and y equals t squared, and then you could graph it. You plug in a t value, you get a first coordinate, second coordinate, and you can get different times. You know, so you do questions like, here are the 2 parametric equations for 2 cars. Would there be an accident? Like, do they occupy the same space at the same time? That kind of question. The Pandora's box we're opening now is that how many input variables can we have on each of our equations? 2. We could have 3, x, y, and z. You could have 4 if you wanted to, right? And how many times can you compose one function into another? Is there any limit to how many times you can compose a function? You could have f of g of x. You could have f of g of h of x, right? But not only can these be single variable functions, they could be multivariable functions. Like g could be a function of x and y. X could be a function of u and v. U and v could be both functions of t. Is there any limit to how many times you can compose a function inside another function? No, there isn't. There isn't. So let's go with what I'm about to ask you, which is this right here. So let's say I asked you this. I said, okay, I gave you z has 2 inputs, g of t and h of t. So both inputs are in terms of t. How many inputs to f are there? 2. There's one input that goes into both of those, and then they generate 2 different numbers that you plug into the function f. The question I have to ask you now is, what happens if we start talking about taking derivatives? What happens if we start taking derivatives? If x is written in terms of t, then you get delta x is dx dt delta t. What the heck does that mean? You've seen this before. This is single variable calculus stuff. If you want to know how much x has changed, how do you do that if it's written as a parametric equation? The rate of change of x with respect to t times the amount t has changed. This is the slope, and this is how much you've gone. Does this kind of make sense? So like how far up do you go? You need to know the slope, and you multiply it by the base of the triangle. And then the same thing is true for delta y. This is the slope with respect to y with respect to t times delta t. Are you okay with this line right here? Does that line kind of make sense? This is single variable calculus. Slope times delta t, slope times delta t. What we're going to do is we're going to apply that to this equation. You've seen this before. What is that? That's the delta z. Do you remember that three-dimensional diagram I said we're going to keep on going back to look at? It's like the box with like the plane and the point. This is the amount z has changed. So the point might start here, but then it changes by a certain amount. This is delta z. This is partial z with respect to x times delta x, partial z with respect to y, delta y. Here's the thing. X and y, this is not new. This is what we've seen before. But x and y are now written in terms of what? T. So look at this. What does delta x equal? Oh, delta x is dx dt delta t. And what is delta y? Oh, it's right here. So what do? We substitute. That's all we're doing is we're substituting. We substitute in, and what do we get? Well, it looks nasty, but it's not that bad. This right here, what is this? That is what? That's delta x. What's this? Delta y. What's in both of those expressions? Delta t. So what can you factor out? And then what can you divide both sides by? Delta t. Well, you could divide by anything, right? But what do we now have? This is what we have. What is so super cool about this? We now have delta z with respect to t. This is dz dt written in terms of, oh, partial z, partial x, partial dx dt, partial z, partial y, dy dt. First quiz question. When do you use this little symbol? And when do you use the d? So when do you use that symbol? When it's a partial. And it's a partial when what?
When you're taking the limit as delta. Wait.
No, you're overthinking it. How many variables are we talking about when we have that nice little symbol right there?
2.
Or more. So there are multiple options, right?
Oh.
This means partial, right? But what about the d's? Single. This is just the derivative, the differential. So that's the difference. That's just what you have to remember. So the key here is, yeah, it's notation heavy. The only thing you need to remember is how to remember what to write, because that's a lot right there, right? That's a lot of squiggles and like the x's and y's. It's really easy to flip it. Here's the shorthand way of doing it. You ready to see a nice little diagram? Well, first, here's the blue box version of what I just said. Am I going to have you prove and do what I just showed you every single time you do the derivative of a composite function in multiple variables? No. You just need to understand the thematics. Do you understand the math behind what I did here? If you understand the math, then you get to use the blue box. The question is, can you remember the blue box? Well, you absolutely will. And can the blue box be a lot bigger than that? Yes. Because how many input variables could we have at each stage? As many as you want. It could be 5, 3, 12. It could keep on going. And then you'd be like, man, that's a lot to keep track of. Here's how you keep track of it. Ooh, neat little diagram. Z represents the start. And T represents the end. That's what I label it as. Could you call it something else? Yeah. This is your input and this is your output. But you start like this. Z is in terms of x and y. X and y are both in terms of t. So if you want to find delta z over delta t, guess what you do? You draw the paths from z to t. So there's one path here. Here's the green path. And then there's a, let's say, purple path from here. So what, oh, that means we have a little bit, 3 minutes left. What does this path mean? You multiply on the paths. So what do you have first? Partial z, partial x times what? Dx dt. And then what's on this path right here? partial z partial y times what? dy dt. And what do you do with those two things? Add them. And that is equal to delta z over delta t. You multiply on the paths, but you have to circle where you start and where you end. Now the thing is, can you expand this type of diagram to as many variables as you want? Just nod your head and say yes. Yes, you can. I think I clipped one in here. Well, let's say I had this. Let me just give you an example of what I mean. You could have z equals f of, let's say, let me find a good one here. Find a good one here. X is going to be in terms of u and v, and y is going to be in terms of u and v. So what's different here? You start with z, and what is z written in terms of? X and y. But what are x and y written in terms of? U and v. So let's say I asked you for delta z, delta u. What paths do I have? There's to u, and where's another path?
C, Y, and V.
Like this. You see those two paths? So what do you write along each of the segments of those paths? The partials, or the direct derivative, right? So this is going to be dz dx, and what's this? Dx du, or partial, and this is partial z partial y, and what's the next one? Dy what? Du. So then what do you write? The sum of the two products. That's all you do. You just do the sum of the two products. Can this method be expanded to as many variables as you want? Yes, it absolutely can.